Hello, everyone. My name is Ahmed Mohammed Abdelmonem. I am assistant professor at Queen Mary University of London, and today I'm going to talk to you about congestion control. So, why we need congestion control? This is the main question that we ask, and this is purely is reason. The pure reason is that our packet forwarding network scores cannot provide any guarantees on the delivery. They just do packet forwarding, and hence they do only best effort service. Therefore, when we have a sender that can send at any sending rate, they can quickly fill up the buffer of the routers or the switches in the network, and therefore they may lead to packet losses, as we can see here. And these will create what we call as a bottleneck links. So these packet losses can be devastating, and this is how it can affect the network performance. So when we have packet losses, we are losing on the useful work that we are sending. So when the sending rate or the goodput, which is the useful amount of data that are getting through our network, are increasing by the increase in the link load from the senders, they reach up to the point that we hit the link rate, and afterwards, if there is no congestion control that takes care of adapting senders to this rate, we're gonna see something as we call as the congestion collapse, because most of the packets are now being lost and there is less amount of useful work getting through the network. So congestion collapse is that when we have too many transmissions due to packet drops and the amount of useful fresh data plummets. Another effect of congestion, not having congestion control, is that we have increase in queuing delay. So as we increase the link load, the queuing delay start increasing because now the buffer builds up, and it reaches a point where you have reached the maximum capacity of the buffer in the bottleneck leg, and then you start getting packet drops. And then your latency will go out of control because you keep, the queuing delay will increase ultimately to reaching high numbers, and it may reach, become unuseful to use this network. So congestion control is a key component that are necessary to overcome these issues. So how we can do congestion control? Normally, congestion control components consist of three main parts. First, we need signals or feedback from the network that there is something wrong. And these feedbacks can be implicit or explicit. Implicit feedback, such as losses, we observe losses or delay becomes increasing, or it can be explicit or sent by the network to indicate there is some problem there. So also we need an algorithm to basically make adjustments, like the famous algorithm additive increase, multiplicative decrease, which allow us to increase and decrease the window based on the signals that we are getting from the network. And then we need also a rate reinforcement, and this is component responsible for adapting or enforcing the rates that are calculated by the algorithm on the senders, so that we keep them from overflowing the buffers. And usually, to evaluate how good a congestion control scheme is, we have two perspectives. We have the network perspective, when we look at how the queue delay works out, how the buffer overflows happen, the link utilizations in the network, and the fairness among different senders, how fair this algorithm lead to allocation of the rate among the senders, and how stable it is. There is also the user perspective that we look at, and from this side, we look at the application response time, the RTT, and the goodput. So these are briefly the main ideas of congestion control. And the problem is with congestion control, we have no one variant or flavor that fits everything. So we have different types of networks with different requirements, and each network would require different kind of algorithm to achieve the objectives of this type of network. So we have Internet WAN with different flavors like TCP, Cubic, Reno, New Reno, BBR, and QAIC. We have data center networks where we have DC-TCP, we have DC-QCM, timely CDC, and etc. There are many algorithms for data center networks. Also for mobile and wireless network, we have TCP, Westwood, Vegas, and Vino, and many other algorithms that are dedicated for this kind of networks. So let's look in detail how these networks, introduce challenges and opportunities for congestion control. So congestion control in internet or WAN or a mobile or wireless network as well, the problem here is that we have a mix of protocols and usually large buffers, and we have long RTTs usually, and it's a network with multiple ASs. There is no single autonomous system that controls it, and we have also interoperability issues where we have different operators controlling them. The opportunities, on the other hand, is that we have always open initiatives and standards that are, put in place by major players such as OpenFlow, OpenSDR, OpenRAN, etc., that allow us to, have better control over the network. We have also, in play now, programmable networks, P4 switches, and smart NICs that allow us to have, more control over the network as well. We have distributed SDN controllers that can come into play and network telemetry. So these are the challenges and opportunities in internet WAN or mobile and wireless networks. And on the other side, we have also data center networks, which are different in the context, where in this case, the challenges is that we have bursty traffic because of the variable type of applications that are deployed within data centers. We have small buffer. The switches deployed in data centers have small buffers usually, and we have very short RTT due to this short distance within data centers. We have also the problem of encast congestion and a kernel bypass that happens usually. So the opportunity on the other side is that we have also programmable networks that, or the P4 switches and smart NICs that can be deployed and allow us to have more control over the network. There is here in this case no interoperability concerns because the data center is controlled by the single operator and he can do whatever he wants with his network. We can also deploy some explicit feedback in this case because the network again is operated by a single operator, and we can have also centralized controllers. So the congestion control in SIGCOMM had long history. We had many papers. It's almost every year we have a paper related, at least one paper or a few papers related to congestion control in SIGCOMM. It started in 1988 with this phenomenal paper by Van Jacobson and Michael Perls. And then we have high band in 2002, we have this paper on high bandwidth slave product. We have also in 2010, the paper on data center congestion control. And we have in 2015, a paper on RDMA, congestion control for RDMA. And recently into 2020, we have a paper on WAN or DC networks. So over the history of SIGCOMM, there are many impactful work that appeared related to congestion control. So what we have this year, we have very interesting congestion control topics. We have papers on fairness. We have a paper on wireless real-time communication. We have a paper on starvation problem. We have a problem. We have a paper on congestion signals used for load balancing, and we have a paper discussing elasticity. So let's look at the first paper here. Cebinae is it's a scalable in network fairness augmentation. And this paper looks at the protocol diversity that are getting overwhelming. And here the authors look at the question that we need scalable and network fairness with this diverse set of congestion control algorithm playing around. So what they do here, they introduce the idea of introducing penalties for flows that exceed their fair share allocation via a novel shaping technique. So what they did is also they try to have this technique to be compatible with all or most of the CC protocols that exist in the internet, and they propose a solution that is deployable on community programmable switches. And they also released a prototype on this link as well. This is the first paper we have in this session. We have another paper on achieving consistent low latency for wireless real-time communications with the short control loop. And here the authors look at the problem that usually we need low latency for real-time communication. in wireless networks, which is quite challenging, especially for wireless networks. And this is mainly because of it's very hard because we have untimely rate adaptations in these networks, and this will lead to inflated control loops or feedback loops. So the proposal is huge, and they try to reduce the control loop by separating congestion feedback from congested queues. So you can have very fast feedback so that your rate adaptations are timely. So they do this by two components. We have the fortune teller that try to estimate per packet wireless latency at the wireless access point, and they have feedback updater that translate and delivers these latency feedback for protocols to enforce rate adaptations. And they had the simulation and Wi-Fi router-based experiments tested to show the effectiveness of their solution. And their solution shows that it improved the app performance by 17% to 95%. We have another paper on the starvation problem and end-to-end congestion control. And the authors here in this paper, they discuss the delay bounding congestion control algorithms. They usually converge to a small delay range in fixed rate bottlenecks, right? And these algorithms usually aim to achieve interflow fairness, but usually, or in many cases actually, they show that starvation still happen, even the goal for these algorithms is to achieve interflow fairness. And because mainly this is when they do delay measurements, they take into account non-congestive jitters. So the problem here is that they studied the delay bounding congestion control algorithms such as BBR, BCC, VIVAS, and COBA, and they found that small changes in estimated delay would induce enormous changes in the inferred rate. And this will lead the starvation of some flows, okay, because of the problems in the estimation. And they find also that, interestingly, that even if you have a perfect estimator, this is not enough because of the non-congestive contributors to the delay that change these or make these estimations still not accurate. So basically, this is a problem they look at and they try to propose a solution for this. And we have another paper called PLB, which is congestion signals are simple and effective for network load balancing. And here they try to use congestion signals for load balancing in the center. So they find that ECMP or WCMP algorithms, or load balancing algorithm, they create hotspots while they find still capacity are still fully unused in the network. And they find that existing solutions are either not applicable, complex, or less reliable. So they consider here the heterogeneity of switches, protocols, and apps in the networks and try to leverage that. And what they propose is that in their solution, BLB, they leverage existing transport algorithm and identify flows that are experiencing congestion. They look at the congestion signals and use that an indication that there is a problem or hotspot somewhere. And then the need to the solution is to repath these flows that are experiencing congestion. And they leverage here IB version 6 flow labels to change the path of these flows. And they also change only in the idle period of these flows, so that they don't interrupt the transport protocol algorithm and create packet reordering. And they have used this in Google within the data center and their backbone networks. And they found that by using it, they managed to drop the utilization imbalances by 60%, and the packet drops by impressive 33%. The last paper in this session is the elasticity detection, a building block for internet congestion control. And this paper looks into the elasticity of flows and how to leverage that in terms of the design of the congestion control algorithms. So the elasticity is that cross-traffic reaction to changes in available bandwidth. So we look at whether the flow would basically increase its rate if it senses there is more available bandwidth and try to take over this available bandwidth. So the question here is that can elasticity be detected at sender with no support? This is the main question of this paper. And they propose here Nimbus. And Nimbus is a system that is used for detecting elastic or inelastic competing traffic using end-to-end delay and rate measurements, simple rate measurements without any support from the network. And what they propose is that to reduce delays, right, if they detect that the traffic, the competing traffic is inelastic, the sender can use delay controlling protocol for both sender and the cross traffic without impacting the throughput. And if the competing traffic is elastic, in this case, they will compete against it using TCP competitive protocols, such as they change to this protocol like Cubic to compete fairly with these kind of traffic that try to take over the bandwidth. So the Nimbus showed that it can have, with this simple rate measurements and end-to-end delay, it can achieve 85% detection accuracy, even with dynamic mix of flows. And the throughput is very comparable to what Cubic can achieve, but delays have been lowered by 60% on the most of the paths. That's it for the session, and thank you for listening, and hope you enjoy this session. Thank you.